Good morning. Continuing on with our motor interface pump controller, we've managed to have the APB controller control the pumps on and off capabilities, monitor the seal leak detect, monitor the over temperature condition. Now we need to tie the controller into an actual motor starter. These are available on our website. If you go to www.ingram.products.com and scroll down to motor starters, you see that there's a family of these available. Motor starters quite often will give us a feedback signal that tells us whether it actually has activated, which is pretty important if we're relying on the controller to turn on the pump and the pump actually never turns on. We take a look at the circuit we've developed so far. And run it very quickly in simulation mode. We see that we have a thermal overload that has to be normally closed to keep the alarms off. We have a leak detector, seal detector. This threshold should be up around 10 volts. It will trigger on at below 7.5. We have a start input that starts a timer, starts your pump. Pump comes on. Then we can have a stop condition that turns the pump off. If for some reason, when the pump is running and we have a thermal overload condition, we have a alarm light come on, start flashing, and a siren that could be activated if this contact hasn't been made. We also have a display showing the current status of the pump and the seal level. So if we clear this alarm condition, the pump will start up again and we'll show the pump on. So now we need to add in the contactor to the pump. First of all, as I mentioned, the contactor will have an output available to tell us whether or not it actually has closed. We don't expect that to necessarily act instantaneously, so there may be a time delay coming back from that signal. But first of all, let's put in a signal to detect when that contact closes. We'll tie this one into input number 5, and we'll call it contact. Well, since that isn't going to happen instantaneously, we're going to have to put in a time delay between the time the pump comes on and when that contact closes. So we use a time on delay block, and we can tie the input from the pump to here. Rather than feeding wires all over our screen, what I can do is go in and put an input and set its property to be looking at the Q00 output, and it's called pump still. And we'll use that to start our timer. Timer itself, we can set the time delay during our development process. Since we're going to have to manually close that contact, let's set that to about 5 seconds. Give us time to get over there and do that. And we're going to use this contact to reset it. So provided this contact is closed within 5 seconds, this output should never go on. To quickly monitor that output to see if our function is working the way we want, we'll just set up a dummy output. We'll start our simulator. We'll satisfy the thermal overload, satisfy the threshold level. We'll start our pump. We'll let our pump start up. We see this goes on. This timer starts timing. And when it gets to 5 seconds, since we haven't satisfied the contact closure, this alarm condition will go off. If we restart that whole process, but this time, once the pump goes on, we'll satisfy the contact closure, and this point never goes on. So that's going to handle the sensing that the contact actually did close. Now we have the problem that we have two different conditions. We want to have this contact closure failure, or the thermal overload, set off the light, so we need to modify this circuitry over here slightly. First of all, we'll get rid of our dummy output, and we'll get rid of this connection here, and we'll put in an OR gate because we have two different conditions. Either one can cause that output to activate. One condition is if thermal overload triggers. The second condition is if the thermal overload or the pump contact triggers it. We're not using the third input, so we'll leave it as low. We'll take this output, tie it to the alarm light, the alarm silent. Running our simulator very quickly, set up a threshold, thermal overload situation, satisfied, we start it. We won't satisfy the contact, and we see that the light starts flashing after it senses the contact hasn't closed. Now we have the problem that we have two different things causing this light to go off and no way to really understand what's causing it from the operator's point of view. So what we'll do is we'll add another human interface display screen. And if you remember, when we take a look at the properties, there's actually two types of displays. We can have a normal page, which is just running information, or a triggered page. We're going to make this one a triggered page. That means when this input goes active, this screen will automatically pop up. The text we're going to put down, we'll call this one thermal. And then we'll put down another block of text and we'll call that contact. Now the operator will be able to tell what's causing the alarm condition. We put two little indicator lights up. This indicator will have it tied to the thermal input, so that's input number 3. And this input is tied to the contact input, which is input number 5. And this is not an initial screen, this is actually a triggered screen. So we'll click on this. The last thing we need to do is tie this point so that when the alarm goes off, the screen will automatically come up. Okay, running the simulator again. We see that first thing that came up was our error screen because we have an alarm condition. If we satisfy the thermal and we satisfy the seal input, we can now start our pump. Time is down. Starts this timer. The contact doesn't get closed, so when that times out, we see that we have the thermal condition satisfied. The contact hasn't been satisfied. So now the operator knows why the lights are going off, and you can go and take appropriate action. If I click that, it clears that error message, and we can go back and look and see that the pump is running and the seal level is okay. So that has shown how we can tie in an auxiliary contact to our alarm system. The last thing I want to do is take a very brief look at doing current monitoring. And we'll do that in the next video. That will give us a preventative maintenance capability, because as the motor starts to wear, the current draw will become higher, and we can use that for avoiding problems in the future. Come back and see us. That will be in the next video. Thank you very much.